I think maybe I need.
You might have to click on the screen.
Yes. Okay. This is a star forming region. This is in actually the Magellanic Cloud. It's one of the biggest and most impressive of these regions where new stars are forming. And the new stars, some of them are extremely hot, short-lived hot stars, and they illuminate everything around them. And that's what you see the cloud, it's reflected light and also emitted light from those. So that's a place of stars forming. This is about Magellanic Clouds are about 150,000 light years from us.
How long is a short-lived star's life?
A few million years. The extremely massive stars, it's kind of counterintuitive, but the most massive stars burn their nuclear fuel the fastest. And so they're the shortest lived. And they're type O and B stars, if you're into type stars. Our stars are G-type stars. And they go through their life cycle very quickly.
How dense are those clouds? If you were to
How dense?
Yeah.
They're much better than any vacuum we can make on Earth. Densities are typically something between 100 to 10,000 atoms per cubic centimeter, and which is a vacuum we've never achieved on Earth, even with the best vacuum systems. Yeah. This is a galaxy called the Cartwheel Galaxy. It's unique. It seems to be showing the remnants of a recent collision. This seems to be an unstable situation. I don't know if anybody's ever worked it out, but it had a recent collision, and this gives us this as an odd galaxy. It's a peculiar galaxy. You'll see some other galaxies around. There's lots of them.
What's the difference between the blue and the red orange?
The color. No. I'm sorry. Remember, these are artificial colors because it's all infrared. But the blue galaxy, it looks like it has younger stars in it. Older stars look more reddish, like Betelgeuse is reddish, and Rigel and Orion is bluish. And those are different mass stars and different age stars. And this is the Crab Nebula. This is the result of a star that exploded with a supernova. And in fact, the explosion was seen on Earth. It was in 1054. Chinese astronomers recorded a bright star in the sky that could be seen during the day for 2 or 3 weeks. And they looked and they recorded where that was. And if you look there today, you see this. And this is the remnant of the star that exploded, because if you measure the speed of the outlying parts of the cloud, it shows that at that speed, it would have been at the center about 1,000 years ago. So this is clearly the result of that. Supernova, we're not going to talk about that. Well, we'll talk about it next time. But it's certain kinds of stars, not the sun, but more massive ones than the sun, will explode in the end of their life. And the explosion is pretty awesome. When a star blows itself to pieces, just as an example, when a nuclear explosion bomb goes off, then it converts, a hydrogen bomb converts 3 or 4 teaspoons of mass into energy. 3 or 4 teaspoons of mass disappear, and it's all energy, and that gives you all the energy of a hydrogen bomb. When a star explodes, it exchanges 1/3 of its mass, thousands of Earth masses, into energy in a second or 2. So it's unbelievable. You know, things are really big in the universe. It's hard to. I know it's hard to grasp some of these things, you know, and I keep trying to think of examples, but, you know, a couple of months ago, I thought it's a long way from the west side to the car wash on 41st Street, but I can tell you that is nothing compared to the universe. Okay, today we're going to talk about 2 things, the cosmic microwave background and the inflation of the universe. Now this changes the direction of our course a little bit from the previous two lectures. In the previous two lectures, we did what I would sort of call classical astronomy or classical cosmology. That is big telescopes, astronomers looking at very distant galaxies and making careful measurements and at the telescope. The cosmic microwave background has microwaves, and it was discovered in a completely different way. And it's more recent. Both of these are in the second part of the 20th century. The microwave background was published in 1965. So we're now bringing things up much closer to the present time. Okay, going over a couple of things. I talked about the redshift last time. That is, the spectral lines of galaxies are shifted because the galaxies are moving. I introduced it as a Doppler shift, and I think that's okay. But a better way to think of it is that as the photon, the light, comes towards us, the wavelengths are stretched by the stretching of the universe, by the expansion of the universe. When you go to Doppler shift, while that explanation is okay and gives you the right answer, when you get to great distances, you get into some trouble. It's hard to get it explained that way. The other thing is, a couple of people pointed out to me that a good example of the expansion of the universe is a balloon expanding in a two-dimensional space. So if you imagine you're an ant or something, or a two-dimensional being on a balloon, then as the balloon expands, and remember, you're just in two dimensions now, the spots on the balloon all get further apart from each other. But there's no center in that space, in the two-dimensional space. Now, we three-dimensional beings could tell the ant, oh, well, of course, there is a center at the center of the balloon, but the ant wouldn't understand that. Well, ants is slightly... Never mind.
Feel like freshman.
To me, there's also kind of an interesting optical thing here. The spots on the little balloon look a lot bigger than the spots on the big one, but they're the same size. I checked it a couple of times. I copied the little ones and moved them, but it's just an optical illusion. Okay, so let me see what's the next thing. So remember in this graph that we showed last time, which shows just an average distance between two galaxies. Remember, as the universe expands uniformly, that if you neglect the local motion, right, the local motion of galaxies, then they all expand the same way with the universe. Everything, space just gets bigger. Right. By that I mean the local motion. I mean the universe is expanding, but I'm walking closer to you, because that's not part of the universal expansion. That's the local motion. I don't think I used the terms for the three results. You got a problem?
Nothing serious.
That's good. Like to tell us what you did.
Just clicked OK and it made that Roger, that bar go away.
Oh, okay. All right. Okay. It turned out that when Friedman did this in the 1920s, the different ways the universe could expand, namely either expand forever, which is this one, or expand for a while and then come back. And remember, we're now in the expanding, where this is now. That was also related to a geometry. And that geometry, I think, is shown in the next slide. This seems to be.
You gotta click on the screen.
Yet again. Okay, well, let's see. I got ahead of myself here a little bit. By the observations in the early 1970s, it was already indicating that we were closest to this universe. See, Friedman did the theories, but he didn't know which one was actually represented the real universe. The observations were strongly suggesting that we were closest to that one. Well, let's see if it will now work. Now it works. And anyway, this is the three cases that correspond to the three Friedman solutions. And again, this is in a three-dimensional representation, but like on the closed one, which is the sphere, we're looking at as though it were on the surface of a sphere. But we're in three-dimensional space, and three-dimensional space can also be curved. But for us, we can't imagine that. Because just like for the ant to really understand the curvature of the balloon, the ant has to think in 3 dimensions, and he can't because he's a 2-dimensional person. And we, in order to fully visualize a 3-dimensional curved space, we have to think in 4 dimensions. How many of you have thought in 4 dimensions? Leonard, his name Lenny, can't even think of his last name at Stanford, says he always asks his class that. There's always 1 or 2 guys who raise their hand and wax class. Okay. Anyway, so those are the 3 ones. This omega is a parameter which is measurable. If it's greater than 1, we have a closed universe. If it's less than 1, we have this open universe. This one's even harder to imagine, but imagine it goes off to infinity. And then there's the flat universe, which is the easiest one to visualize. That's 3-dimensional space, how we usually think of it, not curved. And that's the closest one that the observations are indicating. Okay, now I'm going to follow this a little bit historically. And there was a very important series of papers in 1948 to 50 by Gamow, Alpher, and Herman. And they looked at the idea that if the universe is expanding, then what was it like before it expanded much, when it was much smaller? Okay. And they published a series of papers on looking at the early universe from the point of view of the Big Bang, at a time when, of course, that wasn't even accepted, when that wasn't, when there was still a lot of argument whether we were in steady state or Big Bang universe. And they did this. Gamow was the thesis advisor. Alpher was a student, and I think Herman was a student also at the time. Gamow is a very famous physicist. He's a physicist who first explained in the early days of quantum mechanics how a nucleus decays radioactively to give alpha particles. That was very mysterious, and he was the first to explain that. He was also quite a character. He was a jokester. Well, one of his interesting things he did, he and his wife bought a rubber raft in a store in Odessa in Russia, in the Soviet Union, and decided to leave the Soviet Union by paddling across the Black Sea. And they were intercepted and caught by the Russian Navy or Russian patrol boat and taken in. And they told them, but Gamow told them that they were just going on a fun excursion and they got lost. And that worked. People believed them. Later on, he went to a meeting and left. He also, well, I don't know if I should tell, but he and Alpher, Herman wasn't involved in this, he and Alpher wrote an important paper on chemical reactions in the early universe. And another physicist named Hans Bethe was not involved at all, but Gamow took the opportunity to put Bethe's name on this paper, so it was the Alpha Beta Gamow. I'm glad I got a laugh out of it. Yeah, I told before, when I told my undergraduates this story, they just stared at me. You all know how this goes. Business tell us at party. Okay. So, well, I'm already giving the results here. One of the things they found, let me go with here. Think now of the universe, the expanding universe, as just a box full of gas, or an auto cylinder, which has gas in the pistons, in the cylinders, yeah. And when the piston compresses, the gas gets hotter. And the same process should happen that the gas in the universe, if we went backwards and compressed it, should get hotter. So, oh yeah, okay, oh, that works, okay, good. I didn't do it, I just got this off the web, so that's what happens. Okay, so they thought the early universe should be hot. And maybe very hot when you go very early on. And so their idea was that the early universe was extremely hot and like hundreds of thousands of degrees, millions of degrees. And then as the universe expanded, it cooled and formed the universe that we have today. And they looked at the conditions in that very hot gas to the extent, and we know a lot about hot gases, okay, up to a certain maximum temperature, right? I mean, a lot of that had been studied. And so here's what the early universe might have looked like. I mean, it's an invention. Wouldn't have looked like anything. You wouldn't have survived at 100 million degrees. But this is 100 million degrees. And that is actually still a temperature which we can work with. The center of the sun is at 15 million degrees. The temperatures in the controlled fusion reactors that we're building are reaching 150 million degrees. So that's still a pretty well-known temperature. And at that temperature, there wouldn't be any stars or people or anything like that. But there would be free neutrons, which are listed as N, electrons, protons, ripped apart hydrogen. And there would start being reactions of protons and neutrons forming deuterium, and then also being ripped apart again. So there'd be nuclear reactions going on, beginning to go on. And as we go down colder to 100 million, to 50 million or 15 million, we would get to the nuclear reactions even in the sun. And then in addition to that, there is hot radiation. Right? When you turn on your oven, you get radiation, photons, light, hot light, and that I tried to illustrate with color. So the universe is full of hot radiation, and at this point, the temperature of the radiation is the same as the temperature of the matter. They're in equilibrium with each other. Okay, well, here's my stove, and you can kind of see what happens with radiation. Two things happen as you increase the temperature. At the lowest temperature, you get the least amount of radiation, and you get the dullest color, the reddest color. And as you increase it, it shifts to slightly higher frequencies, and then even to higher frequencies, and you see it becomes more towards the white, more towards the blue end of the spectrum, because you get more photons and at higher frequency. And then here's the hottest that I could get. Okay, so that happens with radiation. And you've also seen another example. It's not a perfect example, but remember when Coke bottles were in bottles and had a cap, and then when you release the cap, the gas would rush out and expand and cool, and you see a little cloud right on top of the Coke bottle. I was looking for Coke bottles to show that, but I couldn't find. They don't make them anymore, so I can't. All right, so okay, so and this radiation, as many of you are probably familiar with, but I'll mention anyway. There's lots of radiation that we see. There's radiation that we don't see, the infrared, microwaves we don't see, but they're the same kind of radiation, just at longer wavelengths. And here's the spectrum. And we have wavelengths. As the wavelengths gets longer, we go from what you're probably familiar with, gamma rays, X-rays in the dentist, ultraviolet you've heard of. And then the visible spectrum is a small region which our eyes are sensitive to. And then you go to longer wavelength, you get to infrared, and then microwave from your microwave oven, and finally the radio. And then what is the rest of all this stuff? There's this shows sort of the typical sizes of the wavelengths. Compare, you know. really long radio waves are as long as the Statue of Liberty. And wavelength, we mean the distance between crests. From here to here is the wavelength. All right. Now, so what Gamow and Alpher and Herman then predicted was that as the universe expanded, going from the early universe to now, the temperature was initially very hot and then cooled to where it is today. And what Gamow and Alpher and Herman predicted was a very interesting thing. That they said that as the universe cooled to really low temperatures, sorry, come on. Please turn off your. As the universe cooled, it reached a point where, I showed the electrons and the protons separate in that hot plasma. As it cooled down to about 3,000 degrees, which is still pretty hot, but a temperature, we're not unfamiliar with, the electrons and the protons would combine to form neutral hydrogen atoms, the kind of hydrogen we're used to. And it would decouple from the radiation, and that radiation would still be there, but no longer tied to the mass, to the matter. And then, as the universe expanded, the radiation would just keep cooling off. And they said there would still be some of that radiation in the universe today, and they predicted it would have cooled down from the extreme, like 100 million degrees, which I showed, but even higher, down to today, about 5 degrees above absolute zero. Prediction in 1948. So this was an important paper published in a major journal and pretty much ignored as far as I could see. People knew about it, but these three physicists seem to have been ahead of their time, and physicists were busy with nuclear physics and elementary particle physics and cosmology. Didn't have a very good reputation at the time, and so their results were largely ignored.
Roger, was the ignorance, the fact that it was ignored, have something to do with the fact that when the paper came out, they did not have the equipment necessary to measure the super long wavelength, so there was no way to verify?
That's right. There was no way to check it. Yeah. That's a good point. The experimental works just didn't exist.
What was the temperature when the hydrogen atoms could form?
About 3,000 degrees.
That's Kelvin.
3,000 degrees Kelvin, but I'm not making a big difference because at high temperatures, Kelvin and centigrade are pretty much the same. All right, and that happened when the universe was 380,000 years old. You'll have to just believe me on that.
Happy birthday.
Now, the next step happened in the early 1960s, 62, 63, 64, and has kind of a complicated history. Two physicists at the Bell Telephone Laboratories. In those days, Bell Telephone did a lot of fundamental research. They've since given up all that, but at that time they were doing this. And their project was to measure microwaves, which were not as well known in those days as today. And their project was, let us see if when we look at microwaves, what can we eliminate all the extraneous interference, different microwaves from streetcars and televisions and everything else, and either eliminate it all or understand where it comes from. And for that, they had this antenna, which is like a big horn, and it's sort of protected from radiation from the ground and from nearby surfaces. And they started making those measurements. And they were very delicate, the most sensitive microwave measurements ever made. And they worked on this. Well, Penzias mentioned that some pigeons roosted in the antenna. And as Penzias put it, they left a dielectric material which interfered with the observation. And so they captured the pigeons and moved them away. But pigeons have this way of coming home again. So they all came back and they got rid of the pigeons, but they're not going to say how. Okay. Anyway, what they then found, something peculiar. They found that once they had accounted for all the radiation they were seeing, there was still some radiation they couldn't account for. Still some radiation left over. And they measured it and they found no matter where they pointed the antenna, it was the same. And no matter what time of day or night it was the same radiation. So that kind of began to eliminate a human source right away. They were very puzzled about where this radiation came from. And let's see, let's see, where am I? All right. And at that, then they didn't know what was happening, but an astronomer, Bernie Berg from MIT, heard about the result. And at the same time that Penzias and Wilson were making these measurements, Robert Dickey at Princeton University, he knew about this prediction of the microwave radiation from the early universe. And he set up an experiment to look for it. He built equipment to look for specifically that radiation. And Bernie Berg heard about this, heard about the Bell telephone result, and said this might be what Dickey's been looking for. And they phone calls and they said Dickey came out of his office and said, we've been scooped. Penzias and Wilson had found by accident what Dickey and his collaborators were looking for. It was the microwave radiation from the early universe. The temperature was 2.75 degrees, not the 5 degrees, but that was understandable because there was a recalibration of the Hubble constant of how fast the universe is expanding. And when you change that, even which Gamow and the associates didn't know about, but when you change that, you get closer to what was measured.
How do they measure the temperature?
Yeah.
It's the shape. This isn't how Penzias and Wilson did it. The best way to do it is to measure the shape of the radiation spectrum. But they measured the intensity, and from that got a temperature. Radiation. It's called a radiation temperature. And they worked at about 7 centimeters in the microwave. So that's close, but not quite the same as your microwave oven. It works at 12 centimeters. And so that this was published, it was immediately understood how significant this was. Penzias and Wilson published their paper saying they had detected this radiation, but didn't try to ascribe it to anything. Dickey and his collaborators published a paper in the same issue next to the Penzias-Wilson paper explaining what it was.
Wow.
And everybody realized this is changed. I mean, I remember the time. Everybody realized immediately this changes everything. Because now, when we have a window to the early universe, when the universe was at 3,000 degrees, when the universe was 380,000 years old, we've never had anything like that before. So this was a transformational observation.
When was this?
1965, paper was published in 1965. And one interesting thing is that, let's see, this is going to work now, is that remember old TVs had this interference when you were between channels and snow. 1% of that is actually in cosmic microwave background radiation. Most of it is interference from sources on Earth, but 1% of that is microwave radiation. So you've actually seen it. Oh, there it goes. So 1% of that is the cosmic background. Okay, now background, let me just mention one thing about what backgrounds are. Backgrounds are really important in astronomy. The analogy is I do it with waves. When you look at the ocean, just normally, right? You see all these little waves, right? Little ripples and things crashing into each other. And you know that comes from all different kinds of things, right? Ships moving, winds blowing across, whales splashing in it. And it gives this kind of mixed up thing. And that's a background. Other kinds of waves, like on the right here, these waves have a specific cause. There's a storm in Alaska. You know what it's from. Or they're even named sometimes like Mavericks or so. So a background is what the microwave background is this background that we see when we see light from a star. That's a specific thing. So that's what backgrounds are, and they can tell you a lot about things. Okay, so a relic from 380,000 years ago. It was predicted by Alfred Gamow and Hermann and verified by observation. It's in this room right now. It's everywhere. And well, I have to talk a little about Nobel Prizes, I guess. Penzias and Wilson got the Nobel Prize for this discovery. But Robert Dicke and his collaborators who were working on it and explained what it was, they didn't. And there was also some bitterness involved because Alpher in particular and Hermann felt they had discovered the cosmic background radiation. They had predicted it. They had gotten it from theory. And but they were kind of too early, right? And they weren't at the right time. And Alpher wrote a paper that was somewhat surprising, bitter about this, that you know, he had done this work. It hadn't been recognized. His career hadn't gone the way he had wanted it to, and so on. So Nobel Prizes can be controversial. And here's the antenna today. It's now a monument. It's being saved. It's turned upside down here, I guess, so it won't fill it with water in the rain, I guess. And but fortunately, it's being preserved because it really is an important thing. This started the modern era of cosmology. Pretty much the rest of what we're going to talk about. And one interesting thing too is the steady state theory, which had been competing, kind of started dying pretty quickly with the discovery of the microwave background, because the Big Bang had predicted the microwave background and explained it. And the steady state had no way to explain it. They came up with various kind of strange explanations. They said, well, maybe it was just there's hot dust and gas all over the universe and it's radiating at us, but that would have to be uniform in every possible direction. And people said, you can look out and you can see it's not uniform, you know. And so the steady state began to decline and go down. I think Fred Hoyle never gave up on it though. But Max Planck, the German physicist who started quantum mechanics, he once said, I never convinced the old physicists about the quantum theory. They just died, you know. So. Carl Sagan had a nice quote, somewhat related to this. In science, it often happens that the scientists say, you know, that's a really good argument. My position is mistaken. And then they would actually change their minds and you never hear their old view again. They really do it. Doesn't happen as often as it should because scientists are human and change is sometimes painful, but it happens every day. I cannot recall the last time something like that happened in politics or religion. That's Carl Sagan. Mm-hmm.
If the Webb telescope using infrared is designed to look back, I think you said 13.4 billion years, could they build a radio telescope in space that could get back farther? Yes,
We've done that at the Covey, and I'll talk to that in about one slide. Okay. Thank you for that question. I won't repeat the question because I'm going to answer it right away. All right. Okay. So let's see, where are we? One of the things you need to realize, yeah?
Related. In my mind, I'm summing this up by saying, when the universe cools, what that actually means is that the population of photons in the universe changes over time and all the short wavelengths ones disappear? Is that a reasonable way to?
No, we have the short wavelengths ones now. I'm sorry, we have the long wavelengths ones. No,
Yeah.
I misspoke. The short wavelength, high energy photons, the wavelength expands and they become low energy photons. The wavelengths expands with the expanding universe. I almost started saying it backwards, but that's not really. Okay, now the other concept that I think we need to kind of think about is that transition from when we had the hot plasma to when the hydrogens combined and the universe and the mass and the energy separated. When the universe is very hot, like in the top here, the free electrons. See if I can make this work. See, when a photon hits an electron, it moves the electron around. So there's a lot of energy change. Okay, there's a lot of energy exchange between the mass and the matter when the electrons are free, because the photons, the light, can jiggle the electrons easily. But then when the universe is bright, and photons don't move very far before they crash into an electron, and the universe is essentially opaque, right? But later, when the electron combines with the hydrogen, then the electron is bound, and the photon can't move it. And then, I think this plays kind of automatically. Let me go back. Okay, see that's when the electron is free, it can move around, and then when the electron is bound, the photon doesn't interact with it. I don't know why the photon pauses where the electron was. Something we don't understand yet. That's something I don't understand about these things. Okay, so that's what you think about. First, the universe for a long time was this intense, bright plasma, and then when the hydrogen combined, the universe, that plasma disappeared. The universe became transparent. Right, it's transparent today. We see all the way 13.8 billion years in the past. So this is what it looked like again. Let's see, where am I here? Okay, and then this happened as it combined, and then we had a period of dark time, and then the first stars and galaxies started to form. So that's the progression of the universe. And so I showed this before, and so different things happen at different temperatures in the universe. Question in the back?
At the time of the Big Bang, it's so hot, and so dense, that there's nothing that can find to make galaxies and stars. Things, right? It's just energy.
At the time of the Big Bang, what I didn't fully understand.
You can't make stars yet.
Right. Before the universe cooled down below 3,000 degrees, you couldn't make stars or galaxies or molecules. Really. Right. It needed to cool down, and then the stars and galaxies form. And in the animation I just showed, where you started with the hot plasma, then there was a period of dark time, which we call the Dark Ages, when there was nothing. And then about 200 million years later, the stars started to form in the galaxies.
Roger, is there a relationship between cooling and the creation of heavier elements, so that the hydrogen is cooling at 3,000 degrees, and it's got just one proton and one neutron, but iron, which is much heavier, would that form when it got cooler? Is there a relationship between declining temperature and formation of heavy elements?
Okay, does everybody hear that question? And did we
Yes.
hear? That is the right idea, except that your time scale is a little off. What happened, and I haven't mentioned this before, is that as the universe cooled down to below 15 million degrees, then heavier elements began to form, like helium formed at that point, and helium is forming in the sun right now. Okay, then a little bit of deuterium formed, a little bit of lithium formed around that millions of degrees, because you need millions of degrees to get nuclear reactions going. Then Hermann and Alpha and Gamow thought that this process would continue, but it actually didn't. The universe cooled too fast and the nuclear reaction stopped. And what was necessary then is that the nuclear reactions started up again in the centers of stars. Stars formed, and the centers of stars reached that 15 million degree mark, and elements formed. That's the whole subject of my lecture next time.
Oh, sorry.
Question. Are you gonna talk about the black hole that they found that's 15 billion light years away?
I'm going to talk about that in the last lecture, those black holes. Yeah. Getting ahead of me, I'm trying to go. Okay, somebody asked if we could build something in space that would detect this. This was the Cosmic Background Explorer, COBE. It was launched in 1989, 1993, particularly to measure the microwave spectrum of the black body radiation. It turns out the Earth's atmosphere is opaque to much of the microwave part of the spectrum. Where Penzias and Wilson and Dickey were looking was in one region where it's not so opaque, where they can come through. But above the Earth's atmosphere, all the microwaves are visible. And this is what they found. And this is the intensity of the radiation versus its wavelength. So it's a spectrum. It's like the spectrum when you put sunlight through a prism. And this is the curve. That is the most microwave radiation comes out at something like a millimeter, a little bit longer. And the line is the theoretical curve with one fit parameter. The theoretical curve for black body radiation, which Max Planck derived in 1900. And the points are the measurements, and they agree perfectly. They agree even better than the points because they had to make the points big enough so you could see them. But in fact, the points lie closer to the curve than the size of these points. It was absolutely perfect. And I was at the meeting where they showed this graph for the first time, and we gave it a standing ovation. So, kind of fun. Yeah. So it was a very memorable thing. So here is now after the COBE measurements, two other satellites, namely WMAP and Planck, were sent up with better instruments and so on. And this is a map across the full sky of the microwave radiation in an artificial color. And it is slightly warmer in the red places and cooler in the blue places. But it's only very, very slightly. Here's what this map is. I mean, if you make a map of the Earth, then this is a map of the sky. It's the same idea. So you get an idea what you're looking at. The point is the difference between the hot and the cold region is 100 thousandths of a degree. 1/100,000th of a degree. So it's incredibly uniform. But and so we'll and later in this talk today, we'll talk about both things, that how incredibly uniform it is, but then the differences are real, and we have to understand those too.
So Roger, so the difference is basically the number of photons in that area, or is it the wavelength of the photons? It's hot versus cold.
Well, those things, it's the wavelength is different. Okay,
Okay.
we're measuring different frequencies.
Okay.
So it's incredibly smooth, deviates by this many degrees, but it's real. So I just said all this. And just to give you an idea of progress in science, the Kobe measurement in terms of seeing how fine a detail it could see. That's what we call a resolution in astronomy. This was its measurement, and then WMAP came across 10 years later, got this, and Planck, which is a European Space Agency satellite, got this. And we think these are actually real sizes. That is, if you go to higher resolution, it'll still look like this. I mean, you might see a little more detail, but basically it won't change a lot. All right, this was another Nobel Prize thing. John Mather and George Smoot, who were leaders of the team, which consisted of thousands of people, the Kobe, got the Nobel Prize for this in 2006. This is John Mather. I went to graduate school with him, and he's one of the nicest guys you could imagine. This is the King and Queen of Sweden. This is George Smoot. And John spoke to us in a talk about 3 years ago. He's now the chief scientist of JWST. He led that whole effort for 30 years to get JWST into orbit. So he's had a very distinguished career. John told me that that in the Nobel Prizes, because Alfred Nobel in his will listed what areas the Nobel Prize should go for, but because he listed physics first, at the dinner, the physics winner sits closest to the king. So that's the protocol. That's how they decide where you sit at the Nobel banquet. I wanted to remember that in case, but you know. Okay, let's take a break. Okay, well, let me go over it again because it's kind of a nice graph because it shows the whole history of the universe in one picture. And what we've talked about now is, see, here's the age of the universe. And what it tries to illustrate is that the universe has expanded. But early on, it was this hot plasma, which are illustrating by the microwave background here. This was at about 380,000 years, when the universe was 380,000 years old. Then we had the hydrogen deionization, the electrons combining, and we had a period of dark ages when the universe was dark. And during that time, the matter started collecting, and then the first stars formed at about, well, it said 400 million degrees, but now the evidence from JWST is it's somewhat earlier.
Is the darkness because gravity from the plasma is so heavy that no light can,
No, there just wasn't any light around. Okay, it had changed. Okay, and then, so these first stars formed, and then the universe evolved. And let's see if I have, yes. So the Hubble Space Telescope was designed to look back to here to something like 500 million, when the universe is 500 million years old or so. That's its earliest time. But the JWST was designed to look at when the first stars formed. That's what's going on right now. That's why we're so excited about JWST, because we're seeing an evolution of the universe that we had never seen before. And that's what it's accomplishing. That's what's really going on. Okay.
Roger?
Yeah.
Didn't you say on a previous lecture that the James Webb has seen some stars actually back at 380,000?
No, I didn't say, if I said that, that's wrong. No stars were there. The earliest things that that the JWST is seeing are galaxies, which are made of stars, but at about 300 million years.
Okay.
And we're trying to, and they're going to push that back a little bit. Because to push it back, basically you take a longer exposure, but they haven't gotten to that point yet. Okay, so push it back as far as we can, but that's where we are right now. Okay. All right, I'll take one or two more questions.
Okay, in the so-called dark ages, it seems to me that you would still have the cosmic background radiation, it would be a lot bluer than it is now, but that would be the only light. And
Yeah.
there wouldn't be any new light emitted, it would
That's
just,
right.
that would just be, your surrounding would be a consistent, sort of a constant,
Yes.
glow.
Yeah. But you're not, it's just radiation.
right,
Okay.
okay.
Okay, well, now let me talk about the second topic for today, the inflationary universe. This is a new topic, new idea. Well, that'll be the rest of the time. I hope I can get through this. The Big Bang has some puzzling problems. And I'll mention two of them. One is the horizon problem and the other is the flatness problems. And just to give you where we're going, these were resolved by a theory which we call inflation. That's where we're going. So the universe seemed to have done something strange. One of the things that was strange was if you look at the universe, and particularly the black body radiation, the cosmic microwave radiation, it's taken 13.7 billion years for those photons to get to us, right? I mean, I'm just leaving out that 380,000 degrees, roughly very close to the beginning. So those photons, that radiation is just getting to us. But if you look at the other side, the other direction, it's the same thing. That radiation took 13.7 years to get to us. But if that's the case, they've never been in contact, right? Because it's taken all that time for the light to get to us, and it couldn't possibly have been in contact before that. So why are they almost the same temperature? Right, there is this small difference, but they're almost at the same temperature. And that puzzled people. If two regions, when here in a room, I bring a coffee cup in here, in a short time, the coffee gets a little bit cooler, and the room presumably gets very slightly warmer, and they come to the same temperature. Now these things have come to the same temperature, but they've never been in contact. That puzzled people. Well, see, you look in the same. You look in different directions, and nearby you see the same thing. You see different things, but in a cosmic sphere you look in different directions, and it's isotropic. That's kind of a far reaching. First, I know the outcome of this, so the buffalo won. Okay. Okay, so that's the puzzling uniformity. So one of the answers at the time was, well, that's just how the universe started. It started the same everywhere. And that's the answer to it. That wasn't a very satisfying answer to people, but I mean, that's like saying, well, the sun is at 5,800 degrees because that's just the way suns are. That doesn't answer much. Okay, the flatness problem was the other problem. I alluded to this earlier. We are very close to flat. And that parameter, see if I did the parameters. Yeah, this parameter here is 1 if the universe is flat. And the number that people measured was 0.3. But it could be anything. Could have been 0.00003, or it could be 100 or 1,000. There was no reason why it had to be so close to flat. And people didn't have an understanding of this. And that was called the flatness problem. And again, some people said, well, that's how the universe started. That's it.
Roger, has the discovery of dark matter and dark energy affected any of this?
Yes. And I should maybe, since you raised it, one of the big things that, and you're not going to like this, but it changes these curves somewhat. The dark energy changes these curves, and it doesn't not annihilate it completely, but there's a sophisticated change that will make, and we'll get to that. Okay, well, Alan Guth had a really good idea in 1981. He was a theorist, and his ideas, he said we could solve all this if the universe had a very brief period of very rapid expansion. not just the gradual expansion that we're seeing now. That was his idea, and he called it inflation. At that time, I think there was a lot of monetary inflation and so he came up with this idea that when the universe was young, I mean, really young, 1/35 zeros seconds old, then it suddenly expanded by this much. I don't even know how to say that number. It's a huge expansion. This is a theoretical idea. So just to give you an idea of this, there's a famous legend of the chessboard. And it said an Indian Maharaja or so wanted to reward an advisor. The advisor said, well, put 1 grain of wheat on the first square and then double it for the second square. And then keep doubling it. And that'll be your reward to me, that much wheat. And the Maharaja said, of course, no problem. But if you actually calculate it, this is how many things of wheat you get. 10 million trillion by the time you had 63 doublings on the chessboard. So, but during the inflation, Booth said the universe might have had 100 doublings more. If somebody might want to check me on this, but I figured out that this is something like 10 trillion bushels or 330 years of all the world's wheat. So even in 1 year, you get this much wheat on the chessboard. Right? So it's a big number. That's what I'm trying to emphasize. Okay, so the inflation explains why the universe is so close to flat. And the reason is, look at these 3 balloons again. The small one is curved sharply, but the big one is curved more smoothly. It's flatter. Okay, so when you get expansion, you go to more flat surfaces, and in the 3-dimensional universe, you go to closer to flat. So, with the, do you understand that? Okay.
But
I mean, and that's the reason people thought that the Earth was flat, because it's round, but we don't see it because it's such a big, the curvature is so gradual on the big surface. Okay. So that's. We don't believe in that theory anymore. Okay. So now the horizon problem is a little trickier to understand. But what Guth proposed was originally at that 10 to the minus 36 seconds, the universe was in a very small region, which could be in thermal equilibrium. That's everything would be in contact with everything else in this tiny region. And then there was this rapid expansion into a much larger region, probably larger than our universe, certainly. And then we're in this situation and the expansion is slower and they no longer have contact with each other. That was the way to get out of the horizon problem. So, okay, I'll see if this works. Okay, that's the rapid expansion. And then there's the slower expansion that we're in now. And that's how you get out of it. Okay, so that's illustrated by this rapid expansion here. And then there's a slower expansion since then. And you might notice that it's curving upward again here. We're expanding a little faster now than we did. We'll talk about that. Okay. I'll be next. I won't be this time.
Question.
Yeah.
Is there any connection with quantum mechanics in this inflation?
Yes. The question is there any connection with quantum mechanics in this inflation? What caused inflation? And people don't have a great idea, but that is still something of a mystery. But what they think is there was a kind of a condensation of water. There's a sudden change in quantum mechanical fields, and that sudden change triggered the inflation. But that is still a theory. That is still an idea that we're not sure. the other thing that came about in this is that when in the quantum mechanics, you have this kind of an event, the stuff in the fields are not smooth. They have fluctuations. And that might be the origin of the fluctuations in the cosmic background radiation. But there, and so you see, the cosmic background radiation lets us see back to 380,000 years, long before this, the galaxies and stars formed. But it's maybe preserving things from events even earlier than that, even further. Okay. That's basically what I'm saying. So thanks for that question, but it was exactly my next slide. It wasn't a planted question. Okay, well, I mentioned this earlier, but don't need to worry about it right now. That cat indicates you don't have to worry about it right now. But right now, there is evidence that the universe is expanding faster again. Nothing like the huge expansion of the inflation, but there is evidence that the universe is not expanding uniformly. Very strong evidence that in fact things are speeding up.
With no idea about why.
That is the question is any idea about why? We think there is a quantity in the universe called dark energy. But we don't really know why. I mean, just because we name it doesn't mean we understand it. And it's a subject of a great deal of investigation now. What is a dark energy? What is the source of it? How will it behave? Does it change? And people are working very hard on those problems. Okay. Well, another thing that came out with these that Andrei Linde, a Russian physicist, and Alan Guth both found that as they studied the inflation more carefully, they found that different parts of the universe could inflate differently. And that has led to the idea that maybe there are other universes around. Maybe there's inflation in different places. It's very speculative. But maybe there's a universe that we don't have any contact with. And you might have heard of this. It's the multi-universe instead of the universe. And so that's really interesting. I actually went to a talk by Linde and asked him, I mean, is there any evidence for this? And the evidence he said is that this is a prediction made by the inflation theory. The inflation theory has worked really well in other places, and it predicts this. So while we don't know that that's really the case, but there's some indication that we're thinking about multi-universes. Okay, well, to end, I wondered something I read that I liked about. If science proves some belief of Buddhism is wrong, then Buddhism will have to change. In my view, science and Buddhism share a search for the truth and for understanding reality. So, in contrary to Carl Sagan's comment, there's a religious leader who's willing to admit that he may need to change. And so I kind of like that. So first one I've ever heard. But so there might be some wisdom there. Okay, so just to conclude, the universe is filled with radiation, and this is a relic of the radiation that filled the early universe. Its temperature, its structure, its fluctuations give us a window to this very early times how the universe evolved. In inflation, the universe had a brief, very rapid expansion by a factor of something like 2 to 100. And it explains several puzzling properties of the universe. And it may predict a multi-universe, but that's pretty speculative. But we have to think ahead. I mean, it's something we can't prove or disprove right now, but maybe someday we'll have some. Okay, and next time we'll talk about the origins of the elements. Yes.
So the rapid inflation must have been going, things must have been separating faster than the speed of light.
Yes, yeah, absolutely.
So they're probably, yeah.
You may not like that, but let me try to explain this. Even if without inflation, we run into that problem. I mean, if you imagine a universe that's uniformly expanding as it is, then, and that means, as we showed in several ways last time, that as you go further and further, things move faster and faster. Eventually they'll reach the speed of light. Doesn't that contradict? It doesn't, because there are two kinds of motion in the universe. The kind of motion we're used to is that when you move from one point in the universe to another point in the universe. Remember that grid I showed? I don't know if I can go back to, right? The grid expands. Yeah, well, what kind of motion? When I walk towards you, I'm moving from one grid point in the universe to another. So that's one kind of motion. But the other kind of motion is that you're locked to a grid point, like a galaxy, and they all expand. And they're not changing the grid points. Einstein's theory of special relativity said nothing moves faster than the speed of light, refers to the first kind of motion. Changing grid points, going from one place to the other. But the expansion of the universe as a whole doesn't follow that. It can go faster than the speed of light. Okay? It's a geometric thing, right? I mean, you just, if I had an infinitely big grid, the things are locked to the grid and the grid uniformly expand, the further I look, the faster it goes, and eventually it goes to the speed of light. But that doesn't contradict Einstein's theory of special relativity. For one thing, no energy moves from one point to the other in this second kind of motion. In the first kind of motion, energy moves from one point to the other. And that's limited by the speed of light. But the second kind of motion isn't. You gotta think about it. These things are.
It is very.
Oh, gosh, people are holding their.
I'll think about it and explain that to you.
People are holding their head. Okay, look, everybody. Here's the thing to me. When we look at the universe at its largest scales and at its smallest scales, the atomic quantum scales, the smallest and the largest, things are not just the same there as they are here.
Yeah.
They're not just the same as here and littler, or they're not the same as here and just bigger. Actually, new phenomena take place that we're not used to, that we haven't thought about, that we didn't evolve with. That's, I think, the tricky thing. See, we evolved, and we're pretty good at hurling rocks at saber-toothed tigers, but we're not good at imagining four-dimensional space, right? We're not used to that. We didn't evolve with that. So that's why you have to really stretch your imagination when we're talking about things like the cosmos, or for that matter, they're very small, which as well. Okay. Well, I forgot what the question was.
Yeah, is matter and energy